Welcome to the lecture session for the tutorial 5 interference of the course Applied Physics UPH004. We have this tutorial sheet, and in this tutorial sheet there are 8 problems. I'll divide this lecture into 2 parts for this tutorial. In the first part we will solve the first 4 problems. In the second part we will solve the next 4 problems. So this tutorial is related to the interference that we have covered in the lecture class, and these are the slides that I have used in the lecture class. So you must have all these lecture slides because I have shared it in the Google Classroom app with you all. So let's start with the first problem. The first problem says two beams are forming an interference fringe pattern. If their amplitudes are in the ratio of 3:1, what is the visibility? So to solve this problem, we have to use one simple formula, though we have not derived this simple formula in the class, but here it is. And that visibility is defined by 2a1 a2 a1 square plus a2 squared. What are these a1 and a2? a1 and a2 are the intensity of the two beams which are interfering. So if in this problem, as it is shown that we are interested into the ratios of the two intensities, so let's convert this formula into ratios. So the formula would convert into a1 by a2. So that's our first ratio, and this is a1 by a2 plus 1. Now we can use this ratio directly in here, and we can get the visibility. So it's 2 into 3, and 3 square plus 1 is equal to 0.6. So the visibility turns out to be 0.6. So that's our problem 1a. 1b, we have given the visibility to be 0.5. What is the ratio of the amplitudes? So in that case, this visibility V is 0.5 is given, and we are to find out this ratio. So what we can do is we can use this expression and simplify it to a useful form, and let's see what happens. 2a1 by a2 divided by a1 square plus 1 is equal to V. So after simplification, what do we do? What do we have? So how do I get to this? So given this V is 0.5, which is half. So here I have replaced this V with half, and then we rearrange and we get to this expression, right? Now this is in the form of a quadratic equation. For this, a1 by a2 is like our variable. So a1 by a2 must be given by, so that's a solution, right? So for a given quadratic equation like ax square plus bx plus c is equal to 0. So for this quadratic equation, the solution is x is equal to minus b plus minus square root of b square minus 4ac by 2a. We use this expression here. So in this case, a1 by a2 is our x, and a is 1, so here 2. B is 4 plus minus square root 16 minus 4. And with this, what we have is the result to be so for this one case with this plus, another case with this minus, we have 3.73 with the plus, and with the minus we would have 0.26, I think. So these are the two results for the ratio of the intensity of the ratios of the amplitudes of the light used for the interference pattern. Now, so that is our problem number 1. For the problem 2, what is the minimum thickness of the parallel film in which the interference of the green component of normally incident light can take place by reflection? So here we are talking about the interference due to a parallel thin film, and the interference is happening due to the reflected light from the parallel thin film. The parallel thin film is made up of a material of refractive index 1.4, and the light that is used is the green light of wavelength 530 nanometer. So, and normally incident light, so incident angle is 0, and that's why the refraction angle will also be 0. Problem number 2. So now we are talking about a parallel thin film. So it's like this. So here is this thin film, and its refractive index mu is 1.4, and the light that is falling onto it is normal, so the incident angle is 0, so the refraction angle is 0. And for such a situation, we have, for parallel thin film, the interference due to reflected light, there are two conditions. One, for minima, the condition is 2 mu t cos r is equal to n lambda, where n is equal to 1, 2, 3, and so forth. And for maxima, 2 mu t cos r is equal to 2m plus 1 lambda by 2. Here m is equal to 0, 1, 2, and so forth. Now this t is the thickness of this thin film. This is the t, the thickness. Now what we are asked to find is what should be the minimum thickness, that what should be the t, so that it remains the minimum for an interference pattern to be seen. So now if we are thinking about minima to be seen, then this formula needs to be used. If we are to see maximum, then this formula to be used. Now let's see, for the minimum, t to be minimum, this n or m should be taken to be minimum. So from here, what we have, so that's for minima. So 2 mu t minimum, r is 0, so cos r is 1 is equal to n. What is the minimum n? N is 1, so lambda. So this implies that minimum thickness that we can have for a destructive interference, that means t minimum is equal to lambda by 2 mu. For the maxima, what do we have? 2 mu t. So m minimum is 0, so lambda by 2. That implies that this minimum is lambda by 4 mu. So given the wavelength and the refractive index which I have used, so here the incident wavelength is lambda is equal to 530 nanometer. So given the wavelength and the refractive index, which is 1.4, lambda is 530 nanometer, we can see that the T minimum comes for the maximum of the interference pattern. So T minimum is to be calculated from this formula. So T minimum is lambda by 4 mu, and that should come out to be is equal to T minimum is equal to 530 divided by, that's nanometer, 4 into 1.4, and this is equal to 94.6 nanometer. So this is the final result for the question number 2. Next, we look at the question number 3. A beam of white light is incident at an angle of 45 degrees on two parallel glass plates separated by an air film of thickness 0.001 centimeter. The reflected light is admitted into a prism spectroscope. How many dark lines are seen across the entire spectrum? Now, to understand this problem, let us make some picture, and that would help us. The diagram for the corresponding to this problem would look like this, that there is a set of parallel glass plates. So this is a glass plate, and this is another glass plate. And they are parallel. Okay, don't mind my not so accurate drawing. And then there is a incident beam which is falling at an angle 45 degrees. And what kind of light is this? This is a white light. And the wavelength of this white light ranges from 400 to 700 nanometers here. In between these two parallel glass plates, there is this medium. That medium is air. So here refractive index mu is equal to 1. What is the thickness? T is equal to 0.001 centimeter. Now with this setup, what will happen? So white light coming in, some part would get refracted into this medium, and then it will be reflected back from the lower glass plate and then transmitted into the medium, and then some part will be reflected right from here. And then these lights will interfere locally here, because here it's a white light. So this light is white. Here is a white light. So here the component of the light are of different wavelengths. So what will happen is, in this region, some of the wavelengths will interfere destructively, and some of the light would interfere constructively. So for all those lights which would constructively interfere, they will come out of this surface, right? And for all those lights which would make destructive interference here, will not come out of this. So let's say here there are only two wavelengths, and one wavelength makes destructive interference here, then that wavelength will be absent in this reflected light, and the other wavelength makes a constructive interference here. That wavelength or that light would come out of this surface. And now the question in the second part of this question, what it is saying, that the reflected light is admitted into a prism, right? That means after it gets reflected from here, what we have a prism here. So this light gets incident on this surface, and after it gets transmitted through the prism, what would happen? It would separate the light into different components. This is the dispersion of the light due to this prism. So now here, if this light are consisting of several wavelengths, then here I will see a spectrum of several wavelengths. If this light are missing of some wavelengths, then those missing wavelengths correspondingly would not be observed here, and they would appear like some dark lines here, 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 all corresponding to the different wavelengths. So that's what the question is, that how many such dark lines will be observed in this region after it gets dispersed by this prism here. So now to solve this problem, first the given wavelength range is from lambda is equal to 400 nanometer to, let's say this is lambda 1, then lambda 2, this is 700 nanometer. So the wavelength of the white light, wavelength of this white light ranges from this lambda 1 and lambda 2. Now let's see, our next step would be we need to find out what are those wavelengths, or how many such wavelengths that comes in between 400 nanometer and 700 nanometer will interfere destructively in this region, right? Now to do that, for a given lambda 1, we have to find out what is the order number of the destructive interference. So how to find that out? We have to use this condition, 2 mu t cos r is equal to, let's say n1 is the order number for the destructive interference, n1 lambda 1. So here n1 is equal to lambda 1 to mu t cos r. So how much is lambda 1? Lambda 1 is 400 nanometer. Then 2 mu is 1, mu, this is the mu, the refractive index of this film, and t thickness is 0.001 centimeter. Then cos r, how much is cos r? Cos r is 45 because the incident angle is 45. So mu is equal to 1 incident angle and the reflection angle would be the same, because here also it's air and then air, glass, then air, so these two lines will be parallel. So refraction angle within this film will be 45 degrees. So this will give us n1 to be is equal to 20. Now similarly for the wavelength lambda 2, we can find out the corresponding order number. So in that case n2 will be 700 nanometer, and this will give us n is equal to 35. Now once we have these two order numbers, the next is in this reflected part of this beam, as it is moving towards the prism, those wavelengths for which the order number lies between 20 and 35 would be absent. And that's why the wavelengths, those corresponding wavelengths would be absent in this spectrum. An absent wavelength means dark lines in this spectrum. So how many such order numbers are possible between 20 and 35? 15 integer numbers, right? So our final answer to this question is that a total of 15 dark lines will be observed in the spectrum after the prism spectroscope. So that concludes our question number 3. And next let's look at question number 4. So in case of question number 4, what do we have? The question number 4 is also very interesting. A soap film is formed using a rectangular wire frame and held in a vertical plane. When illuminated by laser light of wavelength 632.8 nanometer, one sees a series of localized interference fringes that measure 15 per centimeter. Explain their formation and calculate the angle of wedge. So again, we need some diagram to understand what is going on. Yeah. So to understand this, what we have to first look at is a rectangular wire frame, and this rectangular wire frame contains a soap film. So here is, let's say this is this rectangular wire frame, and there are this soap film in between here. So what would happen if such a frame is held vertical? So it's like when you would held it vertical, then it's like you would be looking from this side, and what you will see is this frame like this, if the frame is held vertical. So you will see just a line. However, if this film here is affected by the gravity, so what will happen? That this film would get like this. I am drawing it just as a cartoon version. So what I want to say is that at the top the film would have a minimum thickness, and at the bottom it would have a maximum thickness. So the film would form like a wedge in between, as it is held by this frame here. and this wedge angle, let's say that wedge angle is theta. Our aim is to how much would that wedge angle be. You know, let's think about it again. Why this wedge is forming? Because the soap film is made up of some polymers dissolved into a solution and some other molecular materials, and so that's in a very liquid form. And when you put it vertical, then some of the heavier elements or some of the liquid soap would get affected by the gravity, and they would come downwards, and that's how more soap material will be at the bottom than compared to the top, and that's how its thickness would grow at the bottom and its thickness would be less at the top, and that's how it forms this wedge-shaped film. Now, to understand the next part, that it says that such a wedge-shaped thin film, when you have, then it uses a light of wavelength. That wavelength is lambda is equal to 632.8 nanometer. So this wavelength is incident on this wedge-shaped thin film, and that's a laser light. And when you do that, what you see is here there are a range of fringes of alternative dark and bright and dark and bright. And how many such fringes? So 15 per centimeter on this wedge-shaped thin film. So to understand this, why you are seeing this, so here is our thin film. So let's draw it in another way. So this is our wedge-shaped thin film. This is the wedge angle. Let's say this is theta, and this is the incident light. So when that happens, at every point wherever the light is incident, the thickness is different. Now, for such a wedge-shaped thin film, the condition for maxima or minima interference patterns, so this is for maxima condition, and minima condition is 2 mu t. Also, we can derive that the fringe width, so the distance between alternative dark or bright fringes, beta is equal to, this formula is being derived in the lecture, so we are using it. It says fringe width beta would be 1/15 centimeter. Then from here, what we have, theta is equal to, and this would give, so that turns out to be 3.56 into 10 to the power minus 4 radians. So this is our result. So that finishes our part 1, and in the next part we will look at the problem number 5, 6, 7 and 8. Thank you for having the patience to watch all the problems.